Hi, hello, welcome to VHDL Basics. Today we are going to design a synchronous RAM in verilogHDL. This is the basic synchronous RAM Verilog code. Here if you see, I am having two parameters, address width and data width. Width of the address will be defined using this address width. Width of the both data in and data out will be defined using this data width. And I am declaring the register memory. So here if you see left hand side we need to have the data width of that memory, and right hand side we need to have depth of the memory. So depth will be 2 power 2 power of address width. So in Verilog this is the syntax for 2 power 2 double star and address width. Here if you see, if you take this example, if address width is 8, then 2 power 8 is nothing but 256. So 0 to 255 is the depth for this memory. If we are changing address width to 3, then it will be 0 to 7. If you see 2 power 3 is nothing but 8, and 8 minus 1 is 7. So 0 to 7 will be the depth of this memory. And there are two other port. One is called clock and write enable. So clock with respect to passage of the clock, both read and write operation will happen here. With respect to write enable, if this write enable is 1, then data in will be written into the memory. If write enable is 1, then with respect to the address we are reading the data from the memory, and that will be assigned to the data out. So this is the basic synchronous RAM. Now we are going to see the test bench for this. So this is the basic test bench for that synchronous RAM which we designed earlier. So here if you see, I am declaring address width and data width parameter. Here I am considering address width as 3 and data width as 8. Then I am declaring the inputs as a register, clock, address, data in and read enable. So address width of the address will be defined using that address width parameter, and width of the data in will be defined using data width parameter. Same thing applicable to data out, which is output. So I am declaring that as a wire here. Now I am doing the instantiation of synchronous RAM, where we need to pass address width and data width parameter to that module, and we need to have all the input and output ports in that instantiation. Now I am declaring I as a integer, since I am going to use that I in the for loop actually. And then moving to the initial block, where I'm going to initialize all the inputs, clock to 0, address equal to 0, data in equal to 0, and write enable also 0. Then after 60 nanosecond, I'm going to start writing into the memory. So using this for loop, this is the syntax for loop in Verilog HDL. This is same as C actually. So first inside that bracket we need to initialize that I variable, and then we need to have the condition, and then we need to have the increment of that I. And then it should start with begin, and it will end with the end. This for loop is ended with the end. Now here if you see, I am taking I as a address, so it will increment from 0 to less than 2 power of address width. So address width is 3, so which means it will be incremented from 0 to 7. And then I am putting write enable as 1. If write enable is 1, means whatever data present in the data in, that will be written into the memory. Here if you see, data in I am having assigning to 1, and then I am shifting that 1 with respect to value of I. So first time I will be 0, there won't be any shift. Second time and in the second time it will be I will be incremented as 1, then that 1 will be shifted by left side one time actually. Likewise, at the end of the for loop, I will be 7. So that one will be shifted 7 times in the left side actually. So that is how that is the data I'm writing into the memory, and then I'm trying to read the memory. So in the second for loop, I'm same thing in the for loop. I'm uh, incrementing the address from 0 to 7, so that I am assigning to the address, and then I'm read enable I'm putting to 0. So here it will have all the 8 address in the read. So it will give out the all the 8 data which is present inside the memory. Then I'm again writing into that memory in the all the address space. With respect to data alone, I'm changing here. If you see here data in, I'm putting as all the bits are 1, and with respect to I am shifting that shifting that data into left side actually. I will show you that how the data shift is happening in the simulation result. In the next for loop, I am reading the uh, data whatever we returned the second time, so we can verify that whether we are getting the data as expected or not. And in the always block, I am generating the clock. So here I think clock will be having a 20 nanosecond period, which is nothing but 50 megahertz. So this is the test bench we are going to use for this simulation. Now moving to the simulation result. So this is the simulation result of this test bench. Here if you see clock is generated and address is incremented after some time. So initially data enable is 0, which means reading the memory. So initially there is no data present in the memory. So we are getting that uh, there is no data present in the data out as well initially. So after some time we are trying to write the data. So for that I am putting the write enable as 1, and I am incrementing the address with respect to this, and I am writing the data. So if you see the first um, address is 0 and data will be 1, so that is what written into the memory. Like that second address and will be shifted by 1, left shift by 1, so that's why we are getting 0 here. And in the second address we will do 2 times shift, like that it will have all the data here. And here I am putting read enable to low. Now we will read the data from the memory. So if you see the readout data is coming out, uh, and again I am going to write the data into the memory. This time I'm changing the data into all the bits as 1 for address location 0. Then I'm doing left shift by 1 and 2, 3, 4, 5, 6 and 7. So these are the data written into the memory. Now I am trying to read the same after once we return into the memory. I am trying to read. So for that I am putting read enable as low. So here if you see data out is happening. So this is the basic synchronous RAM design. Here we can do we can have a separate write enable and a separate read enable signal as well, and we can have the valid for data out. So these are the improvise we can do with respect to the synchronous RAM design. That will help for when we are trying to integrate this synchronous RAM into our actual design. Thanks for watching this video. Please like, share and subscribe this channel for more.